All right, in the first half of section 2.2, we talked a lot about computing volumes of solids by a particular method that we called slicing, where you place the solid on the x-axis and you form slices of it that are perpendicular to the x-axis, and you look at the areas of those cross sections. The area of those cross sections is some formula that depends on x, and you can integrate that formula from the left endpoint to the right endpoint of your solid. In the second half of section 2.2, we're going to be talking about a particular application of the method of slicing, and we're going to use it to compute the volumes of these solids known as solids of revolution. So we'll talk about what those are here as we kind of explore the particular example of a sphere, which is the example that we ended section 2.2 part 1 with. So if we want to rethink about the sphere, maybe first what we want to do is we want to think about this region here between the x-axis and the curve y equals the square root of r squared, and I think we used a capital R for our sphere, so let's use that here. So this is supposed to be a semicircle. Let's see if we can draw a slightly better one. A little bit better. And so this is our curve y equals square root of r squared minus x squared. It's the top half of the circle. And we want to take the region O, and here's why I want to use a lowercase r, because I want to call the region between the curve and the x-axis here, a region we're pretty familiar with. I'm going to call that region R. And what we want to do is we want to take R and we want to revolve it about the x-axis so that it does a full revolution. We want to take it and we want to bring every point in that purple shaded region there, and we're going to bring it in a full revolution around the x-axis. So you can think about pulling it out of the page towards you, keeping that x-axis fixed and just kind of rotating it all the way around. If we do that and we kind of let each point trace out a path through three-dimensional space there, then what we end up with is that all of the points that that R passes through form the sphere. So we get the bottom half of the circle because it passes through the bottom half of the plane, but it also comes out of the page towards you and out of the page away from you as well. So this is one way that we can create the sphere, by taking this region R and just rotating it about the axis. And what we want to do is we want to talk about how can we take advantage of this process of knowing something about how the solid was formed in order to compute its volume in a reasonable way. So maybe take a moment to remember what we did with computing the volume of the sphere. We looked at these cross sections formed, and when we intersected a plane that was perpendicular to the x-axis with the sphere that we formed, we got a little circle. Now, the circle, if we look at kind of that picture in the plane, was both the top half of the circle that we started with and the bottom half of the circle that we started with. And this shaded region here became a vertical line in the plane. And the nice thing was the height of that vertical line was exactly the y-coordinate of the point on the circle, and so we were able to talk about the area of the cross-section by knowing something about the height of this line here. And that's exactly the process that we want to generalize here, beyond just using this for a circle, also talking about a general curve that lives above the x-axis here. So let's think about what's going on here. If we have some function, f of x, we want it to be a non-negative function, meaning that this word non-negative here says that f of x is greater than or equal to 0. In other words, f of x is above the x-axis in terms of its graph. So we have a non-negative function on an interval a to b, and we want R to be the region bounded by the graph of y equals f of x and the x-axis. So let's think about what our region R is. It's going to be very similar to what we had before. So we know that if we have some interval here from a to b, and I have the graph of my function f of x, I know it's above the x-axis because it's a non-negative function, and we want to think about taking this region R to be the region bounded by the graph and the x-axis. So okay, so it's the region between the graph and the axis here. So again, a region we're pretty familiar with. And we want to take this thing, and again, we want to revolve it about the x-axis. So we're going to take every point here, and we're just going to bring it all the way around, full 360 degrees. If we think about the shape that we get by doing this, we get, well, on top it kind of looks like the graph of f. On the bottom it looks like the negative of the graph of f, and in fact that is what it is. Let's see if I can draw that here. There we go. And everywhere in the middle, we kind of have circular cross sections here. The circles are larger for larger values of y, and they are smaller for smaller values of y. All right, not a fantastic drawing, but it's what we've got to work with here. All right, great. So we have some kind of solid of revolution that we're formed by revolving this about the axis, and we want to talk about what exactly the volume of this solid is. And again, what I'm going to do is I'm going to use the method of slicing. So we're going to take some plane which is perpendicular to the x-axis here, and we're going to look at the cross-section that it forms. And we just finished saying that those cross-sections are circles. And we want to find a formula for the area of that cross-section. So we know that the cross-section is a circle, so its area is going to be pi r squared. The question, of course, is what is the radius of the circle that we've drawn, and because it should depend on x. So if I go here to my picture and I think about what exactly this red circle corresponds to in this picture, it's going to correspond to a vertical line which forms the radius of the circle. So if we think about the full circle actually goes down below the axis as well because we've rotated this thing, and so we have a mirror image of f of x sitting down here. So the radius of this circle then is half of this red line, or in other words, it's really just the top of this red line here. So how long is this? Well, the length of the radius here is exactly equal to the y-coordinate on the curve. But the y-coordinate on the curve is given by f of x. And so what we can conclude then is that the area here of this cross-sectional circle that we've drawn is pi times f of x squared. Another way of thinking about it, perhaps, is if I were to create a small rectangle here, perhaps with width dx, then what I could do is I could say the volume of this small rectangle, or the area rather, since we're thinking about this as a two-dimensional shape. We want to think about revolving this this rectangle that I've drawn about the x-axis. If I revolve that area, that rectangle there, then what I end up getting is a disk. That disk then has width or height equal to dx, and it has radius equal to f of x, and so its volume is exactly equal to pi times the radius squared, so pi times f of x squared. Remember, this is a cylinder here, and we know that the volume of a cylinder is the height times the area of the base. The area of the base is pi times f of x squared, and the height of this cylinder is dx. So what I want to do in order to compute the volume of this solid of revolution here is I want to add up the volumes of each of these disks, or each of these cylinders. What that comes down to is integrating this function here, this pi times f of x squared dx, because that's the volume of one of my tiny little cylinders. Again, the way that we represented this with the slicing method was thinking about just integrating the area function here with respect to x. So in the end, the volume of this entire shape was equal to the integral from the left endpoint, well, that's x equals a, to the right endpoint, that's x equals b, of the volume of one of these disks, which is pi times f of x squared dx. So simply by looking at this nice region here that we're familiar with, the region formed by the area between the curve and the x-axis, we're able to compute the volume of the solid that we formed by revolving this curve about the x-axis. So let's write that down. This is going to be called the disk method for computing the volume of a solid of revolution, because the little tiny pieces that we're looking at are disks. Just like we saw with those cylinders there. So here we're going to start off with a continuous non-negative function. We need the fact that f of x is continuous in order to be able to talk about what its integral is. We need it to be non-negative in order for this region to make sense in terms of revolving it about the x-axis. And we're going to let R be the region bounded by the graph y equals f of x and the x-axis. And we want to talk about the volume of the solid formed by revolving R about the x-axis. And just as we had before, this volume is going to be the integral from a to b of pi times f of x squared dx. Great, so let's see a little example here, or maybe even two examples. First, we want to let R be the region bounded by the curve y equals 1 over x, and the x-axis over the interval from 1 to 5. Compute the volume of the solid of revolution formed by revolving R about the x-axis. So this is exactly the setup that we have in the statement of the disk method. In terms of a picture, we're looking at the interval from 1 to 5. Our curve y equals 1 over x, we know in general looks something like this. And since we're just looking at this on the interval from 1 to 5, we're kind of going to cut ourselves off here. Our region R is bounded by the curve and the x-axis. So we have something that looks like this. And we want to revolve this about the x-axis, giving us a solid which looks something like this. Great, so we have some kind of funny looking cone here. And in order to compute its volume, well, we have a formula for it. It says take the function which forms the upper bound. That is the function, so here my f of x is 1 over x. And what I want to do is I want to integrate from 1 to 5, since that's the lower bound on x is 1 and the upper bound on x is 5. And I want to integrate the function pi times f of x squared. And doing a little bit of work, I know that pi is a constant that can be factored out. I still have the integral from 1 to 5. 1 over x squared is x to the minus 2. And so now I can integrate this. This is pi times x to the minus 2. We increase the exponent by 1, so we're going up to x to the minus 1. Divide by the new exponent, minus 1. Evaluate from 1 to 5. So if I do this, I get, let's see, minus pi over 5 minus a negative pi over 1. So that's going to be pi minus pi over 5, which is 4 pi over 5. Great, so we have a nice formula for the volume of this solid, 4 pi over 5. Of course, the x-axis isn't the only axis about which we can revolve regions. We could also revolve them about the y-axis. So let's look at an example problem in which we do that. If R is the region bounded by the y-axis, the curve x equals 2y plus 1, and the lines y equals 0 and y equals 3, we want to find the volume of the solid formed by revolving R about the y-axis this time. So a slightly different setup here, but it's symmetric to the case in which we're looking at revolving things about the x-axis. So if we think about this region here, and with a lot of these problems, I highly encourage you to draw the region before you actually do the problem. It's really going to be helpful to have the ability to visualize what you're doing before you actually start doing it. So we have this region R. We've got it. One of the bounds is the y-axis. Another of the two bounds are the lines y equals 0 and y equals 3. So we know that maybe here's y equals 0, maybe here's y equals 3, and those are the horizontal lines formed at those points. And we also have the curve x equals 2y plus 1. So to form a curve like this, I'm going to maybe think about, well, what happens when y equals 0? When y equals 0, x is 1. So that curve is going to maybe pass through this point here. And as I increase y by 1, x increases by 2. So if I go up 1, I have to go over 2. And so that means that the curve looks something like this. So that is my x equals 2y plus 1. Maybe let's put these other curves, or these other lines here in, let's do red. So that's my y equals 0, and here is y equals 3. So this region that I'm looking at then is the region bounded by these 4 lines that I've drawn. And if you work through it, you can see that that region is this guy right here. And now what I'm doing, instead of revolving this about the x-axis, I'm going to take this and revolve it about the y-axis. So I'm taking points here and I'm rotating them in this manner. So I'm sort of swinging it about this flagpole, which is the y-axis. And so now what I have is I have horizontal circles, or horizontal disks rather, and the volume of each one of those disks is, if I were to draw it here, I would have some disk. My height of this is going to be some quantity dy. And the radius of this disk is now going to be the x-coordinate on the curve, if I've drawn this picture right, which it's a little bit questionable. So if I want to, the thing that I want to integrate to find the volume here, well, I'm going to want to integrate my y values. My y values are going to pass from 0 to 3. And now what I want to do is I want to find the volume of this little disk that I've drawn here. Volume is the area, which we've said is the x value. Let's see, the volume of the disk is the x value times it's the area of the circle, which is pi times the x value squared, since the x value is forming the radius of this circle, times dy. Now, fortunately, the x value at every point that we're interested in here, which is the right end of this solid, is going to be given by this formula, x equals 2y plus 1. The right end point is always that line, so we can think about that x value as simply being twice the y value plus 1. This is the volume of one of my little disks, and so this is the function that I want to integrate here, pi times 2y plus 1 squared. Sanity check to make sure this integral makes sense. We only have one variable, and it's y. Everything else is some kind of constant, so we're good to go ahead with our integral. We can factor out the pi. The integral itself, we have maybe a couple of options for doing it. We can either do a U substitution and think about u as being 2y plus 1. That's a pretty reasonable strategy. We could also expand out the polynomial here and write it out. I think maybe that's the approach that I'll take here. So let's actually, no, let's do the U substitution. So let's do u equals 2y plus 1. And so du is going to be 2 dy. So, which is to say that du over 2 equals dy. And so we have pi here. We're going to have a u squared. We're going to have a du over 2. And we're integrating now. If y is 0, that corresponds to the u value of 1. If y is 3, that corresponds to the u value of 7. And now we have, let's see, so increase the exponent by 1. We still have the pi sticking around out front. So that's going to be u cubed. Divide by the new exponent. We also have a 2 in the denominator, so that's going to combine to give me a 6. And I'm evaluating from 1 to 7. So this is going to be pi times 7 cubed over 6 minus pi times 1 over 6. All right, if we wanted to take the time to figure out what 7 cubed was, we probably could. But in the end, this is some nice volume that we get here. All right, so let's go ahead and again state kind of this process that we just did with revolving about the y-axis instead of the x-axis. As I mentioned earlier, it's very symmetric to the case in which we're revolving about the x-axis. So we're going to let f of y be a continuous non-negative function. So maybe the note that we want to make here is that a non-negative function, when we're thinking about it as a function of y, means to the right of the y-axis. It means, again, that f of y is greater than or equal to 0. And since we're thinking about f of y as being the x values, non-negative x values live to the right of the y-axis. So we have a continuous non-negative function defined on the interval ab. Let R be the region bounded by the graph of x equals f of y and the y-axis. Then the volume of the solid formed by revolving R about the y-axis is the integral from a to b of pi times f of y squared dy. That's exactly what we did in example 2, where our f of y was this 2y plus 1 function. And we exactly integrated pi times 2y plus 1 squared dy.